Hey everybody, I'm Julius Rauscher and I am proud to present to you our paper called SkiVis, Visual Exploration and Route Planning in Ski Resorts. Skiing is a very popular winter leisure activity, with 400 million skiers hitting the slopes yearly worldwide. Depending on the expertise of the skier, he or she has preferences towards different slopes. The enjoyment of skiing or snowboarding heavily depends on choosing the right slope. However, with ski resorts increasing in size, finding the most favorite slope becomes more and more a trial and error process. Slopes are typically color-coded by difficulty, labeling easy as blue, intermediate as red, and advanced as black in Austria and Switzerland. There also exists a variety of lift types, most notably a T-bar, which can be challenging for beginners, chairlifts, gondolas, and cable cars. However, even slopes in the same difficulty classification can widely differ in terms of geographical properties such as steepness or width, meaning that every slope is unique and no two slopes are alike. Furthermore, current ski resort information systems do not provide routing capabilities. This led us to investigate the following research questions in our paper. How can we visualize a ski resort as a geospatial network while effectively incorporating individual slope properties? And how can we facilitate preference-based routing capabilities within a ski resort? We follow the general guidelines of an application paper and present the following contributions as part of our work. First, we surveyed the current state of the art and in collaboration with domain experts conducted a requirement and task analysis for modeling a ski resort. We further present a visual analytics application to explore and navigate a ski resort as our main contribution. We evaluate the application through a usage scenario as well as a user study. And since the domain of ski resort visualizations is rather unexplored, we provide a list of open research opportunities for future work. Virtually all ski resorts depict their slopes on a panoramic trail map, which distorts the underlying geography in favor of artistically depicting the landscape. Field investigated the applicability of a different schematic map based on a metro map design. In his study, he concluded that the prevailing panoramic design is too established for alternative designs to succeed. Regarding routing in ski resorts, Friedsam et al. Provided a basic routing system, however do not consider a user-centered approach for which incorporates individual preferences. As part of our requirement analysis, we met with domain experts comprising of experienced skiers and ski guides and asked them about the currently available tools and their limitations. Their responses concluded that contextual information about slopes is often neglected, and routing features, such as Google Maps, is not available. Together with our experts, we elicited a set of features that define the slopes of the ski resorts and grouped them either as static or dynamic features. For our analysis, we decided to neglect the dynamic features for now, as they are difficult to obtain reliably and are mostly only available for the entire resort and not on an individual slope level resolution, hence having no impact on the preference-based routing as of now. The tasks that we thus defined are exploring a ski resort according to a set of features, provide a ranking based on preferences towards these features, allow routing between two arbitrary network points, and integrate preferences into the routing algorithm. Here you can see our application interface, which models Ski Arlberg, the largest ski resort in Austria. It consists of a topographic map as its core and a number of linked components, which we will introduce in the following. We opted for data from OpenStreetMaps, as official resort data is difficult to obtain and the usage of VGI data allows easy transferability to other resorts. From OSM, we obtained the slope and lift data and segmented them into 30-meter segments for a closer inspection. To enrich the data with steepness, altitude, and compass direction information, we used the DEM to pre-calculate these features for all of our segments. VGI GPS trajectories helped us to estimate the popularity or crowdedness of a slope as well as the average travel time. We chose a double line approach as our base visualization for the slopes where the outer line visualizes the difficulty classification and the inner line the actual steepness of the segments. The color scale is oriented along the Austrian norm for slope classifications, with the exception that steepness values below 0 are colored in green. This allows us to expose uphill segments on slopes, as the example on the black advanced slope here shows. In case of ungroomed slopes, the outer line is styled with circles as to mimic a mogul slope. A tooltip provides the requirement of context information for each slope, allowing us to closer inspect the steepness profile or the compass direction of the slope. Further information about total ascent or descent or an travel time estimation is also given. The route summary on the bottom of the interface provides a sequential view of the currently shown route, including altitude profile and slope number indications. As it is linked with the map view, a brushing interaction can help with following the route along the map. The preference widget allows the user to input their preferences, such as finding rather unpopular slopes. A number of presets for different skier expertises are also available. The list of best matches presents the user an ordered list of slopes which he can further inspect or mark as favorite and thus add them to the routing. To facilitate the routing, every slope is assigned a specific cost, which is adapted to the user preferences. Here, we leverage attribute scoring functions to transform the difference between the preference value and the actual slope value to a score between 0 and 1. With the preference-weighted cost, we can use Dijkstra's algorithm to find the most suitest way between 2 points and make use of the traveling salesman problem to find the optimal route between different favorited slopes. The application offers 2 different workflows: an automated workflow where the user only inputs the start and end location and the duration of the route, or a semi-automated workflow which permits the user to interactively select and sequence their favorite slopes. The workflows are presented more in detail in the following usage scenario. Jamie is an experienced skier who annually partakes in skiing trips. This year, he visits St. Christoph in the Ski Arlberg region for the first time and uses SkiVis to guide her through the resort. As a first step, she selects the advanced preference configuration to explore the resort. From the list of best matching slopes, she can identify several slopes fitting her criteria. Being unfamiliar with the resort, she initially opts for the automated workflow and desires a route recommendation for 2 hours duration for a morning run before returning to the hotel for lunch. Driven by her domain knowledge, she sets her preferences on compass direction to the southern-facing slopes, as she prefers to ski on sunny slopes. For the afternoon, she decides on the semi-automated workflow to generate a trip of around 2 hours duration. She enjoyed the 52 Kandahar-Galzig slope from her morning run and marks it as one of their favorites as she wants to ski it again. She also selects the 5 Gamberg Direkte slope, a slope from the list of best matching slopes that did not make it into the automated suggestion she followed in the morning. She's further looking for an ungroomed, north-facing slope, knowing the snow conditions are better preserved with lesser sun exposition. By adjusting her preferences accordingly, she identifies a number of possible candidates. After carefully investigating her options, she finally decides on the Bachseite slope, as it does not include any uphill segments and adheres to the time restrictions. With an estimated duration of 130 minutes, she is happy with the suggestion and finalizes the route planning. As a form of quantitative evaluation, we conducted an online user study by using online conferencing software. We interviewed 6 domain experts with at least 10 years of skiing expertise, 3 of them being certified ski guides of the resort and 3 being completely unfamiliar with the resort. In the first phase of the study, the subjects were introduced to the application before being asked to interact with it themselves. They had to perform a number of tasks aligned with our requirement analysis, namely an exploration phase and 2 route creations, each following one of our workflows. The study was concluded with a think aloud interview. Findings from the study conclude that the subjects were content with the color scale as it helped them to identify undesired uphill segments. Furthermore, the experienced guides concluded that the routing recommendations were appropriate. Care should be taken, however, when recommending free riding routes, as fatal accidents can happen here when not taking the necessary precautions. We added a disclaimer to our application when recommending these slopes. A requested feature from the subjects was the integration of bus routes and restaurants, as these activities complete the experience of an entire ski day. Lastly, the subjects voiced skepticism when transferring the recommendations from the application to the real world, as no guidance for making the right decision at an intersection is provided. During the study, a number of derived use cases, which could also be investigated by SkiVis, became apparent. One finding in the study was that a lot of slope segments are deviating from the given difficulty classification. With a little adaptation of the color scale, segments being steeper than the classification can easily be identified by red color indicating danger. Segments which are less steep than the classification are visible as blue. Although being intriguing, this design leads to confusion as the colors red and blue are already established by the skiing context. Another derived use case is the analysis of skier behavior from the GPS trajectories. Several research questions can be investigated by leveraging this information, namely, which paths do freeride skiers take? Where are stopping points along the slope? How wide is the slope at which segments? Or where are inaccuracies in the OpenStreetMaps data? As the domain of ski visualizations is rather unexplored, we encourage further research by providing a list of research opportunities. Context-aware routing would include snow and weather conditions into the routing algorithm. When tuned perfectly, a majorly sunny route could be found on a cloudy day, or a cleverly timed restaurant stop could be inserted during a bad weather period. With more fine-grained temporal GPS data available, temporal resort dynamics could be exposed, where patterns in traffic flow or snow quality could be investigated. As skiing is an activity typically carried out in a group, a collaborative route planning feature could determine optimal routing strategies for multiple users with different preferences. Lastly, a community-based annotation method within a social network framework would bring skiers together and let them share information about snow qualities, hazards, accidents, or long lift queues. With that, I want to conclude my talk. If you want more details, we refer to reading our paper.